All right, good evening, students. It's Mr. Rich. Welcome to another Sunday night math Q&A. I'm going to work your math homework problems. If you're one of my students, you have my email address and you can send me one or two of your homework problems. I'd be happy to work them for you. I do have a few that have already come in. I'll keep my eye peeled for any more that come in. It looks like we're going to start with some AP pre-calc problems. So I will pull those up. If you're not one of my students and you're joining on YouTube, you can put something into the comments section and I will see it. If you are here, go ahead and put a note in the comments so that we know that you're here. And then let me pull up the first problems. So, all right, so go back to me full screen and I will pull these up. Thank you. And Olivia sent in a few questions. So let's take a look at those. All right, hopefully I can read these. This looks like it might be a little faint. So I will pull it up, see what you all think. We might need Olivia to resubmit these. Okay, so you can go back here. I think we might be able to make these out. All right, so you can go back there and display my screen. All right, that looks pretty tough. All right. All right, I'm going to read it. I think I can make it out. A stone is thrown with an upward velocity at 14 meters per second. Yeah, all right, so 14 meters per second from a cliff that is 20 meters high, maybe. The stone's height is modeled by the function h of t equals, I can tell what that is. I'll write it. It looks like it's negative 4.9 t squared, oh boy, plus 14t plus 60. Olivia, if you can grab another photo of that and send it in. Yes, send it. Yes, okay, thanks, Olivia. So resend that. All right, Chrissy, go back to me full screen. I'm going to pull up the next one here. Christina is my assistant here helping us maneuver through here. So let's go. All right, so Hadley sent a few in. These are also AP pre-calc. And Olivia's going to resend those so we can see it because that's definitely a problem that we want to work. And let's get back here. This one looks like it's in a couple of different parts. I think she said that she had to send it in. Yeah, so there was it's a multiple choice question. And now, while I'm pulling this up, if you are watching this and you've got any homework problems, submit them. Okay, you can take a picture, and I guess if you don't have my email, you can't really send a picture, but you definitely can type your question into our YouTube comments, and then I can slap it up here. All right, so here, go ahead and take me back to full screen. Or not me to full screen, but back to my share my screen. There we go. Well, what we have is a rational function, and they give us this g of x, which is x cubed plus 1,000 over x squared minus 100, which then has been factored into x plus 10, x squared minus 10x plus 100, x squared minus 100. Which of the following statements describes the behavior of the function g? Well, if we take a look at the answer choices, they're talking about where it might cross the x-axis, where it might have a hole, or where it might have a vertical asymptote. All of these being at either x equals negative 10, x equals negative 10, x equals 10 and negative 10, or it has no holes. So they're talking about the zeros that are going to be in the denominator, because holes and holes in vertical asymptotes are going to come about by having zeros in the denominator. Now, graphing the x-intercept, graphing the x-axis is going to be related to the zeros up in the numerator. However, so here's what we're going to do. To make full sense of this, we are going to graph our denominator. So we'll leave the top here. This does not look like we can factor it any further. I'm talking about this trinomial right here. But this is the difference of two squares in the denominator. So here's what happens. When you factor this into x minus 10, x plus 10, we are going to get these two binomials to divide out. That definitely tells me that we have a hole located at x equals negative 10. When you have two binomials that are factors that are going to divide out or cancel out between top and bottom, we now know that that's the location of a hole, or what we call a removable discontinuity. All right, so definitely we're not going to get a 0 at negative 10. So A is out. So I'm liking answer B. It tells us that there's a hole at x equals negative 10 because x plus 10 appears exactly once in the numerator and exactly once in the denominator when both the numerator are factored. So that's probably going to be our answer. But on the AP exam, or on AP questions, generally speaking, multiple choice, pre-calc and calc, consider all of the answer choices. Let's take this all the way down. So we definitely can say C, we do not have a vertical asymptote because the x plus 10 got removed. So C is out. And it says the graph has no holes because the degree. So yeah, that's just a totally false statement right there. So we have answer B. All right, take me back to full screen. I'm going to go grab another one of Hadley's questions. So let's do that. And I see Olivia resent that. Excellent. And all right, so let's bring the next one up. So again, this is going to be a pre-calc question. I'm not sure if this one is, maybe it is also going to be a multiple choice. So I'll grab these multiple choice options and slap them up here. And then I think there should be one other one. Okay, Hadley, I think I lost maybe answer D, but that's okay. All right, so take me back to my shared screen, and we'll take a look at this question from Hadley. All right, thank you. So it shows the graph of a rational function R is shown at with a hole at the point 1, 1/2. Which of the following statements would be true about a hole, I guess, located right here? Neither the limit of the function as x approaches 1 from the left, right? So this is a notation that is new to you pre-calc students, right? This is saying the limit of the function r of x as x approaches the number 1 from the left side. So that superscript with the minus means from the left. Superscript of a plus sign next to that value of 1 means to come in from the right. Now it says neither of those limits is defined. Now I can tell you that's false. One of the things that we know is that when we take a look at this, the limit as x approaches 1 from the right, this function is called r of x. So we'll say the limit of r of x. The closer that you come, as you're coming in from 1 from the right-hand side, the closer you get to the number 1, the closer you're getting to a y value of 1/2. So that limit is 1/2. But that's also going to be the same answer as if you're coming into 1 from the left-hand side, because as you're coming along the function and your x values are approaching 1 from the left-hand side, you're getting closer and closer again to the y value of 1/2. So that means then that the limit as x approaches 1 from the left. The limit of my function is also equal to a 1/2. And when both the right-hand side and the left-hand side limits are equal to the same value, the limit overall at 1 will exist, and it will be 1/2. So we can get rid of this because it says neither are defined. No, they're both defined, and they're both equal to 1/2. It says neither is defined, but the limit as you approach 1 is defined. I don't think that is true because these are both defined, and therefore that is defined. That's how it works. If both of these are defined and they are the same value, then that means the two-sided limit, that is the limit as x approaches 1 overall, will be defined, be that same value. All right, and then C is both are defined, but these limits are not equal. So I think the answer here, Hadley, is D, which is the one answer choice I don't think I got, or if you did send it, I did not see it. So this should be both these limits are defined. The left hand and the right hand limits are defined because there is a hole, and the overall limit is also defined, and they're all equal to 1/2. Okay. All right, let me go grab Olivia. So take me back to full screen. I'm going to grab hers. Thank you for resending that. Olivia, I'm not sure that one was any better, but let me take a look. It is, let's see. Oh, okay, she did sign. Okay, I see. Very good. So, yeah, let's do this. I'm just going to, I think I could maybe highlight that. I think I can do a copy paste. All right, take me back to my screen share. Yeah, this is going to work. Okay, very good. Here it is. A stone is thrown upward, is thrown with an upward velocity of 14 meters per second from a cliff that is 20 meters high. The stone's height is modeled by this function. How high is the stone at 3 seconds? When will the stone reach maximum height? When will the stone be 10 meters? When will the stone hit the ground? Now, Olivia, this is probably, I'm going to say that this might be a calculator active problem. So what we would do for answer A is it's just saying plug 3 in for T. So to answer A, we're just going to say what's h of 3. And so we would do minus 4.9 times 3 to the second power plus 14 times 3 and then plus 20. All right. Now, normally, if this is a pre-calc, I think this is pre-calc. This seems like it doesn't feel like a pre-calc question, but yeah, with a calculator. So let me show you what your teacher wants you to do with the TI-84 calculator. What we're going to do is we are going to put the function that they gave us into our y1 equation in our equation editor of the TI-84. We're going to use x as our variable, but I'm going to type negative 4.9. And I'm going to show you several ways that you can do this. A couple of features that you want to know how to use on your TI-84. So we're going to put negative 4.9 x to the second power plus 14x and then plus 20 and then enter. So we've got it in there. And now I double check, right? So when you're using your TI-84 for any calculator active problem on a test, you need to double and triple check that what you just put in there is what the question called for, right? Because it's very easy. I will make a mistake probably 25% of the time. I will type it in there wrong. And I'm never going to come back and look at it again. So I need to make sure before I leave and hit second function quit that, that I've got it in correctly. Now, the nice thing about our calculator is that we can call up that function and use it from our home screen, right? This is my calculation screen where you normally type things in to do a calculation. But if you hit alpha trace, this button right here, it pulls up this menu that allows you to pick one of those 10 functions that are entered in there. Where our function is in Y1, so we're just going to hit enter. And then using function notation, we can put the number 3 in parentheses, and we will pass that value for x up to that equation. And when I hit enter, it'll calculate and it'll return the value. So on a free response question, we would say h of 3 is equal to 17.9. And we know that this is going to be height, right? H is height in meters. So that's going to be 17.9 meters. The next question, part B, says, when will the stone reach its maximum height? I could do this. I'm going to show you how I would do this just knowing about standard form of a quadratic. One of the things you should know about quadratic functions that are written in standard form, which is what we have here, ax squared plus bx plus c, is that the vertex is going to be at negative b over a, 2a, negative b over 2a. That is a formula for what we call the axis of symmetry for the parabola if its equation is written in standard form. So looking at this equation, we know that b is 14, so we'll make that a negative 14 over 2 times a, and a is negative 4.9, so we can put that in right there. And so what I'm going to do is I'm going to do that calculation. I'm going to make a fraction on my home screen, negative 14 over 2 times 4.9, and that's a negative 4.9. So let's go ahead and put that in. I'll put a negative in there. And that means then that is 1.429. And since that's an x value or a t value, that is going to be in seconds. So when will the stone reach a maximum height? After 1.429 seconds, because that's the x coordinate or the t coordinate, since our independent variable is t. That's when it's going to reach its maximum, because that is where the vertex is located. Now, what we could do is I want to show you how to do this graphically. Like, suppose you wanted to graph it and actually look at where the vertex is. So here's what you have to do. I'm going to come in here to graph the parabola that I put in here for this y1. Is I am going to hit the window button, because I need to set the window. And I'm going to set it starting my x values, which are representing the t's here. I'm going to start it at 0 because that's when the rock was thrown. And I'm going to go out to about 20. So 20 seconds. I'm telling the calculator how far I want the x-axis to go out in the window. And then I'm going to set the y min, and I'm going to start that at 0, ground level, and we'll go up to 20 as well. All right, so once I set my x min, x max, y min, y max for the window, I can go and hit the graph, and then I see that. So it doesn't look like we're seeing enough, definitely. So what I'm going to do is we need to set this window to make it much higher. So I'm going to go to 100. I think we can go, I'm going to change this to maybe 20, but I need to go up to 100 on the Y max, and let's graph it and see. All right, so it went a little too high. So it'd be nice if I could just pinch this with my fingers like it was an iPhone, but I can't. I have to change the window manually. I don't recommend using zoom on this. Okay, I'm going to cut this back to 10 and cut the Y max down to about 40. And then regraph it. Okay, so that is the vertex. We're looking at it. And here's the height when the rock was thrown, which was at 20 meters. What you need to do to find what we call that a relative max. So what I'm going to do is hit second function trace and tell it that I want it to find a maximum value. So I'm going to hit enter. Now notice it's asking me a question. It says left bound. It wants me to move the cursor along the function, and I need to move it to the left until I can see the cursor pop back up into view. There it is. Notice I was watching my X's and Y's down here, and I had to bring this X back. And I'm going to move it to the left because it wants me to be left of the maximum that I just told it that I wanted to find. And then I hit enter, and then I move it over to the right of the maximum and hit enter twice. And you can see it gives me a value there of 1.429, which is what we calculated already. All right, so if you know that formula, it's a much easier calculation than having to graph it and find that maximum of 1.429. Now, what this also tells me is that the maximum value or the maximum height of the stone, you can see it right here, is y equals 30. So it didn't ask me for that, but they could have asked me what is the maximum height, and that's the y coordinate when t reaches 1.429 seconds. All right, so let's move on. When will the stone be 10 meters high? That means that I'm supposed to set 10, that h of t equal to 10, and then I'm going to solve this equation for t. But here's what I'm going to do, students. If I'm going to tell the calculator, I'm going to use the calculator to solve this for t. And if you've ever studied how to use a graphing calculator to solve an equation, what you do, or one of the things you can do to solve this equation that we've just generated, is to graph the left-hand and right-hand side equations separately. In other words, I'm going to graph another function, y equals 10, a horizontal line that would come straight across, and see where it intersects the right-hand side function. So I'm going to go back to y equals, and y2, I'm going to put the left-hand function, y equals 10, in, and still graph at the same time the right-hand side. And then just hit graph, and I will see that there is that line y equals 10. That intersection point is the solution, or I should say the x coordinate of that intersection is the solution to this equation. So how do I find an intersection point on the TI-84? I do second function calc, and I want to find an intersection. So I'm going to hit 5 until it find the intersection. And again, it says, am I on the first curve? Well, you can't see the blinking cursor because it says x is 5 and y is negative 32. So it's way down below our screen. So I'm going to come left. So yeah, I'm going to tell it, yes, you are on the first curve. I hit enter. And now it says, am I on the second curve? And I'm like, yeah, there's only 2 curves, but yeah, so that's the second curve. And it says, do you want me to guess? Meaning run the algorithm to find that intersection. I hit enter. And there it is. It found the intersection point. So the solution to this equation is t is equal to 3.449 seconds. That's the answer. So I used a graphing approach there. Now, I got to show you this, right? I mean, the TI-84 is great, but it's not great as compared to Desmos. If I did this problem on Desmos, I would have had it done 5 minutes ago. I could graph y equals negative 4.9 x to the second power plus 14x plus 10. I could then graph y equals 10 as my second function, just like I did on the T84. I can come here and click right there. Okay, it gave me a different answer. Why did it do that? 14, did I get that in there right? Negative 4.9 x squared plus 14x plus 10. And then I graphed the right-hand side. All right, let me go back to my T84, see what the difference is. Okay, wait a minute. Okay, I just simply rewrote that incorrectly. See that it started off as a plus 20. I just wrote it down as plus 10. So I'll go back to Desmos. And not that Desmos, that Desmos. let's change this to the right number, plus 20. That was the original function. And now you'll see 3.449. It shows me that intersection. So same process on the TI-84 in terms of I'm graphing the left and the right-hand side of the equation, looking for the intersection point, but it's much faster to do it in Desmos. But that won't help you on your tests in class because you'll be stuck with the TI-84. All right, and then part D, when will the stone hit the ground? Well, that's when will the height be 0? So then I'm looking for the x-intercept. So what I'm going to do is I'm going to take a look at the graph. I'm going to change this window here, students. I'm going to change the window so that the y-min is a -1 because I definitely want to be able to get my eyes on the x-axis. So I'm going to make the y-min -1. So when I graph it, you can see where that x-intercept is down here. I'm going to change it. I want to see more of it down there. It's a little bit too close. So I'm going to make this -5. Graph it. There we go. Now I'm going to do second function, calc. Tell it to find a 0. I'm looking for the x-intercept because that's what I'm doing. I'm setting the equation, right? I'm solving the following equation. 0, the height is 0, equals -4.9 t squared plus 14t plus 20. So I'm going to tell it on my TI-84 to find the 0. And again, it wants to be left bound. So I need to be left of the x-intercept. So I'm going to get right there, just left of the intercept, hit enter. I need to go to the right and then hit enter twice. And you can see it's 3.903. Desmos, all I got to do is click and it shows me 3.903 is right there. All right, that is it for Olivia's problem. Thank you, Olivia, for sending that in from your pre-calc class. I am taking a look to see if there's anything else that came in. I don't see any emails that have come in. So what I'm going to do is I'm going to go into working some other AP pre-calc. I know a lot of my students that need help that come here are looking for AP pre-calc help. So I'm going to work some problems from 1.7 to 1.11. And this has to do with rational functions. So the students taking AP pre-calc, and I'll tell you, if you're in Algebra 2, you'll be studying some of this. You're welcome, Olivia. You will be seeing these problems in the spring, these rational functions. So you might want to watch this and see what we're doing. But when you're in AP pre-calc and you get to sections 1.7 to 1.11, it's a lot of it is a review. It's a complete review of what you studied in the spring called rational functions, where you had to find vertical asymptotes, horizontal asymptotes, holes, x-intercepts, y-intercepts. But there's a few wrinkles that we throw into it. And I will tell you that the problems on your summative, on your test, will be much more challenging than what you ever saw in Algebra 2. All right, so you have to be, and I'll say it again, I say it to all my AP pre-calc students, you want to be working problems in AP Classroom. That is where you're going to get the level of difficulty that you are likely to see on your test that your teacher is going to give you. And I go so far as to tell my parents and the students that if your teacher is not releasing AP pre-calc, AP Classroom problems for AP pre-calc, then you need to ask your teacher, please, could you go into AP Classroom and release some practice problems, multiple choice and free response, because that's what you got to practice on. If your teacher's giving you stuff in Delta Math on rational functions and you go in and you do them all, that's great. That helps you understand the foundational parts of rational functions. It's not going to really help you too much on those harder problems on the test that you're going to get. So let me go over some basics and then also show you some AP style problems. All right. So here is the first thing that I want to show you. I want to take a look at a function. This is a rational function. And the first thing that this is asking about the left and right end behaviors. But I want us to go ahead and take a look at this and see if we could determine what the if there are any horizontal asymptotes to this. Now, what we did in Algebra 2 is we said that we want to look at the highest degree terms on both the top and bottom, and that's going to dictate whether we have a horizontal asymptote. So the highest degree terms here are 2x squared over 3x squared. And when we have the same degree on the top and bottom, then we know that we are going to have a horizontal asymptote at the ratio of the coefficients. So there is going to be a horizontal asymptote for this function at y equals 2/3. Then what we're teaching you, though, that's different in AP Pre-Calc from Algebra 2 is we want you to use a limit statement to communicate that there is a horizontal asymptote at that line. So if you come in here and you would say it this, that the left-hand end behavior is the limit as x goes to negative infinity, meaning that if you trace the function all the way out to the left-hand side of the graph, the limit of our function h of x has to be equal to 2/3. And then the right-hand end behavior would be the limit as x goes to positive infinity. And the limit of the function would also be equal to 2/3 because of there being a horizontal asymptote at 2/3. Okay, so those are the end behaviors. If we come over to Desmos and we actually graph the function, which is a good idea as you're doing practice problems, make sure that what you're doing analytically matches up with what you would see if you were to graph it. So we'll put this function in, and we'll see what the end behaviors look like. 5x plus 7. All right. So there's the function. Okay, as we go way out to the right, you can see that it is flattening out, and way out to the left, it's also flattening out. Now, is it at 2/3? Here's how we could check. Let's graph the line y equals 2/3. And sure enough, when you come over here and you go way out to the right, you can see that the function is getting closer and closer and closer to that horizontal line at y equals 2/3. So yeah, we have this right. That's why we're saying as x goes to infinity, as the x's are getting bigger and bigger, those y values are getting closer and closer to 2/3. All right. And so that is, those two statements are confirming, or they're how we state that we have a horizontal asymptote. All right, let's go and do. All right, take me back to full screen. I'm going to go grab a few more things here, and that I think will be helpful to the students that are in pre-calc. Okay. Grab these worksheets over here. While I'm doing this, if you are one of my students, send me an email. You've got my email address if you have any homework questions. We've got a good 20 minutes left here. I'm just doing a little bit of AP pre-calc. Okay, Chrissy, take me back to my screen. All right, thank you. Here's a rational function. What I want us to do is come up with all of the features. This question here is asking us for the zeros. Where are the zeros on this function? So what we'll do is we are going to go ahead and factor the top and the bottom. So this is going to factor into x minus 5, x plus 4, and the bottom is going to be x plus 5, x minus 4. All right, I'm not going to go into how to factor quadratics. I assume that you know how to do that and do that fairly quickly. Well, notice that there are no factors that are going to be dividing out between the top and the bottom. I have no matching binomial factors. So there are going to be no holes. If I have a function, a rational function, where I have a matching binomial factor between top and bottom, that's going to create a hole as long as this thing gets removed, right? So, but nothing's getting removed from the denominator. So that means that both of the zeros for those two factors, x equals -5, x equals +4, those are vertical asymptote equations. All right, so now so we got two vertical asymptotes. We'll make a sketch of this on our own, and then we'll verify it over in Desmos. We also know in terms of horizontal asymptotes that we have the same degree on the top and bottom. I got x squared. So that means I'm going to have a horizontal asymptote at the ratio of their coefficients, and that would be 1/1, or y equals 1. Now, as far as this question, zeros are going to come about after we have simplified and canceled any binomials between top and bottom. They will come about if I have a remaining binomial on the top. And I do. I have an x minus 5 and an x plus 4. So this function will be equal to 0 when either of those two binomials are equal to 0. So when I set that numerator equal to 0, it's going to be x equals 5 and x equals -4. When I set the numerator equal to 0, that means I'm going to have x-intercepts at 5, 0 and -4, 0. And there we go. So that's what we have there. As far as a y-intercept, we could find that very easily because y-intercepts are found by taking h of 0. So if we stick 0 in for x, we see that that's going to be equal to -20 over -20. It's equal to 1. So we can draw a pretty accurate sketch just based on those characteristics. So I'm going to draw a really crude sketch over here. The vertical asymptotes are out here at -5, over here at +4. The zeros are at 5, 0, so there is an x crossing over here at 5, and another one over here at -4, right here. We also have a horizontal asymptote here at 1, so we'll put that horizontal asymptote right there. And what else do we have here? That is pretty much it. Now, this one is going to be a little harder to know exactly what's going on, although to the right of this vertical asymptote, the function is very likely doing this, coming down towards that vertical asymptote. And then over here, since there's no x-intercept to the left of -5, I'm going to change my color here. This one is probably coming from this horizontal asymptote up to that vertical asymptote. So we've got this one coming from along that horizontal asymptote down here. Now we've got to figure out what's going on in the middle. Very likely what's happening is this function is coming up here, and there's a y-intercept at 1, which is interesting. -20 over -20 is 1. So very likely it's crossing and doing this. Let's see if that's right. We're going to graph this and see if that is what this looks like. So we'll do y equals x squared. Y equals x squared. There we go. X squared minus x minus 20 all over x squared plus x minus 20. Okay. And I think you can see, I think we got it pretty good right there. I'll bring this over so we get a better look at it. We'll kind of rescale that. Yeah, so that is what we kind of drew there. So I'll draw the asymptotes. We said we had a horizontal at y equals 1, and sure enough, it crossed the horizontal asymptote right there at the y-intercept And then we had these x-intercepts we said at -5. So I'll put x equals -5 just so we can see that asymptote there. And the other one was at x equals 4, I believe. Yes. So you can see the two vertical asymptotes, the horizontal asymptote. So that's a pretty accurate sketch as to what the behavior is of that function just based on analyzing it. Now that all comes from algebra 2, right? If that is confusing you and you're like, I've never seen that before. Well, all I can say is you either didn't see it or you didn't learn it in algebra 2 or you just totally forgot it and you need to go back and refresh it. That's where delta math would come in. Definitely delta math. It's a good way to relearn a lot of these concepts for rational functions. Now, let me show you a few things. Let me make sure, see if any other questions came in. And I don't see any. All right. So Chrissy, take me back to full screen. And now I want to show you some AP style questions. So I'm going to pull up what you might expect to see on AP problems. And here we go. I thought we might have some AP Calc students here. Okay, Chrissy, you can take me back to my shared screen. I thought there might be some AP Calc students who wanted to come here and get some help because I know they have a test this week, but no questions have come in. Well, let's look at this. They give us a graph of a rational function. And you can see that there is, let's take a look at the graph and look at the features here. So you've got a vertical asymptote here at x equals 4. So that's the equation of the vertical asymptote. There is a horizontal asymptote at y equals 5. And then notice that there is a hole right here at x equals 6. And what they want is they say, which of the following limit statements about f is correct? So let's take the statements one by one. This first statement here says that the limit as x goes to -infinity, right? This means as you go way left on the graph, the y values get close to 4. Well, let's see if that's true. If we go way out to the left, the y values are not getting close to 4. They're getting close to the number 5. That would be a true statement if that 4 was a 5. Okay, so false, but that's also going to be false, make B false, because also you can see as this function's heading out to the right towards positive infinity along the x-axis, the y values would be getting close to that horizontal asymptote at 5. So that's false. This is describing behavior at a vertical asymptote because this says here that as you approach 4 from the left side of 4, it's going up to infinity. So let's see, what does that mean? That means that if you are to the left of 4, right, here's x equals 4, to the left of 4 over here, so we'd be on the graph here, it says the closer that we get to 4 are the y values going up to infinity, and indeed they are. So that statement, as it's climbing towards infinity along the y-axis, that's true. This is false, D. It would be true if this was -infinity. Because as you approach 4 from the right-hand side, you can see that the function coming into 4 on the right-hand side of 4, it's diving down towards -infinity along the y-axis. Okay, so that is what that is all about there. So just to recap, as you head into a summative maybe in 1.7 to 1.11, I think is where you'll probably have your next test, is that you want to know that these have to do with horizontal asymptotes as you go out to -infinity and infinity. But if you come to the one side of an x value and it's going to infinity, that's going to be the location of a vertical asymptote. Now that you would agree, that is new from what you saw in algebra 2. We were not using these limit notations unless maybe your teacher was at AP Pre-Calc and they taught you that in Algebra 2. It's not likely. So anyways, that's new notation for you. Let me show you a few other things. Here's another graph equation where they show you the graph of a rational function, and then they want you to determine what could be the graph. Okay, so very much, could you have seen this in Algebra 2? Maybe. But what do they tell us is true? Well, they tell us there's a vertical asymptote at 3. Yeah, I can see that. There's a hole at x equals 5. There it is. Sure, right? The x coordinate there is 5. There's a 0 at 1. Yep, there's your x-intercept right there. And a horizontal asymptote, horizontal line at y equals 1. Makes total sense. Well, what am I looking at here? In order for there to be an asymptote at x equals 3, that means that in the denominator, there must be an x minus 3 factor that remains even after I simplify it. So when I look at my answer choices, based on the fact that there needs to be an x minus 3 to create the vertical asymptote at 3, A is out because there's no x minus 3 in the denominator. Right? It's not the numerator. It's not factors in the numerator that are going to create holes in vertical asymptotes. It's always the ones that are in the denominator. So we've eliminated that. For there to be a hole at x equals 5, that means there must be an x minus 5 factor on the top and an x minus 5 factor on the bottom. That takes out D. While it does have the x minus 5 on the top, there's not one that would cancel it down in the bottom. And that also gets rid of C. So B, by process of elimination, is there, and we haven't even considered the horizontal asymptote. Now, as far as the horizontal asymptote at y equals 1, every one of these functions has the horizontal asymptote. So that is not a differentiating feature between the graph and the equations. Now, how do I know they all have vertical asymptotes at 1? Because all of these answer choices have highest degree terms, top and bottom of x squared. If you multiply those all out, they're all going to be x squared over x squared, which means there is a horizontal asymptote at the ratio of their coefficients, which would be 1 over 1 or 1. All right. Let's do one more here. I want to show you this one because this one is one that if you don't look at a problem like this and you see it on the test, it might really cause a lot of confusion. This says that we have a rational function that has a hole at x equals -4 and a vertical asymptote at -5. So that means that in the denominator, there should be an x plus 4 factor and an x plus 5 factor. So when you take a look at these, you can see we got x plus 4s and x plus 5s all over the place. Let's see if we could eliminate any that don't have an x plus 4 that will remove a whole, or excuse me, remove an x plus 4 from the denominator. So when I look at answer choice A, there is an x plus 4 and an x plus 4. So this does have a hole at x equals -4. Answer choice B. All right, based on the hole at x equals -4, it can't be answer choice B. Don't see x plus 4 over x plus 4. Now, here's the interesting thing about C and D. Notice that there are, I'm going to zoom in here on answer C. So there is going to be a hole at x plus 4 because this x plus 4 will get divided out by one of the two x plus 4 factors that are in the numerator. That does create a hole at x equals -4. Let's take a look at answer D. Well, what happens here is this x plus 4 gets eliminated, but it still leaves an x plus 4 down here in the denominator. So therefore, there's not going to be a hole at x equals -4 right here. So we can get rid of answer choice D. And where does that leave us? It leaves us that we've got, based on the hole at x equals -4, A and C are still alive. However, vertical asymptote means I got to have an x plus 5 that remains in the denominator. And I do not have that on answer choice A because there's only an x plus 5 on the top, not on the bottom. So that takes us to C right there. Now, I do want to remind you something about there being a hole at x equals -4 right here. Notice that this x plus 5 cancels one of those. So there does remain an x plus 5 in the denominator. So that's why I do have a vertical asymptote at x equals -5. But when we find holes, sometimes we need to find the y coordinate of the hole. So if you do have an x plus 4 that cancels and the x plus 5's here, look what we're left with. We were left with one x plus 4 factor on the top and one x plus 5 on the bottom. So there's the hole. The hole was at x plus 4 because we canceled them, and there's the vertical asymptote. But if I needed to find that y coordinate, I would put the value of -4 back into the simplified version of the function, which would give me 0 in the top and 1 in the bottom. So the y coordinate of the hole would be at -4, 0. So it's setting on the x-axis. The hole is right on the x-axis. So let's graph that and see what it looks like. So coming over here to Desmos, I'm going to graph the original function, x plus 4 to the second power times x plus 5 over x plus 4, and then that's times x plus 5 to the second power. And it's a good idea when working in Desmos to put a y equals here. All right, we said there was an asymptote at -5, so let's put x equals -5 just to see if that is indeed. We'll get it right here. X equals -5. There it is. So yeah, that sure looks like we got the vertical asymptote right. And there should be a hole at -4. And yeah, so what we'll do is we will come over here. Yeah, you can see right here. Let's zoom in on that and let's see if there's a hole. Now Desmos won't show the hole because it's really, holes are infinitely small, if that makes sense. But when you come right here to where x is -4, if you drag your cursor and land right at -4, it does show you the hole and tells you that the function is undefined. So there's the -4, 0 coordinates for the hole. Okay, and zooming back out, that is the function. Notice that we do have a horizontal asymptote here because, well, let's see what our degrees are, right? The degree on the top, this is going to be an x squared times x gives us an x cubed. X times x squared right here also gives us x cubed. So sure, we should see a horizontal asymptote at the ratio of those two coefficients at y equals 1. If we type y equals 1, yeah, we see that our function on both the left and right side is going to be approaching y equals 1. Okay, now one last thing that I want to show you before we go, it has to do with horizontal asymptotes. I think I may have shown you this last week, but I want to show you to you on number 5 right here. And the reason I'm showing this again is because a lot of teachers don't explain to you how to determine the end behavior of this rational function. End behaviors of rational functions have to do with whether there is an asymptote, a horizontal asymptote, or whether the function's going up towards infinity or down towards negative infinity out on the extremes on the left and right. Well, what you want to do is just determine what is the leading term on both the top and bottom if you were to totally multiply this out. See, this would give me a 4x squared. I'm sorry, if you square 2x squared, it gives you 4x to the 4th times the other x would give you a leading term of 4x to the 5th on the top. Down here, you have x squared times x, which is x to the 3rd. So there is no horizontal asymptote because The degree on the top is bigger than the degree on the bottom. So no horizontal asymptote. Now, what will the end behaviors be? Well, it's going to be, if you simplify this ratio, it's 4x squared, which you know is a parabola, means that on the extremes, it's going up to the right and up to the left because it's a parabola with a positive leading coefficient. So the end behavior of this function that we're looking at, this rational function, its end behavior is the same as this. So I know what that is. It's going up to the right, up to the left. So I can say, of course, there's no horizontal asymptote, but the end behavior is that the limit as x goes to infinity of s of x is infinity because it's going up to the right. And then the other end behavior as x goes out towards negative infinity is also going to be going up to the left towards positive infinity on the y-axis. Well, students, I think that is going to wrap it up for tonight. And again, if you're with me and I didn't do any of your homework problems, it's because you didn't send them to me. So send them to me next week. If you're my students and you're here, you've got my email address. It comes to you every time I send the notification that I'm about to go live. You can send me pictures of your problems there. Okay, so do that. If there's anything that I can do to help you in terms of tutoring, I do individual one-on-one tutoring with students. I also have an AP pre-calc group that meets Sunday nights at 9 o'clock right after my live session here. Let me know if you're interested in joining the AP pre-calc group that I have. It's a small group. We've got maybe 5 or 6 students in there, and we do a live session every Sunday night. So if you're interested in that, if you're prepping for the SAT in December or for the October or the November, I think there's a November or December SAT, let me know because I'm also doing group sessions and one-on-ones for all of those. All right, everybody, hope you have a great week at school. Keep studying hard in your math classes. Don't give up. If you're in AP math, it's not going to be easy. But don't give up. That's the whole thing. And your teachers will see if you're putting forth the effort, and they will give you some grace along the way if you keep at it and keep asking questions, keep working hard. All right, everybody, I hope to see you here next week at 8 o'clock, same time, same place here on YouTube. Take care, everybody.